Earth has an invisible shield protecting our planet, but what if it suddenly vanished? At first, the change would be silent. No flash, no crack in the ground. Above us, the sky would look almost ordinary. But far beyond the blue, a vast region of space would begin to rearrange itself. The magnetic bubble that surrounds Earth would weaken, compress, and, if the field truly disappeared, largely collapse. This is not a forecast. Earth's field does weaken and strengthen over time, and it has reversed many times in the planet's history. But there is no evidence that it is about to switch off. So this is a controlled thought experiment. What would happen, step by step, if the field vanished suddenly? To understand the answer, we first need to see the shield itself. Earth is a planet with a hidden engine. Its field is not a painted shell, and it is not a permanent bar magnet buried inside the world. Most of the field is generated almost 3,000 kilometers beneath our feet, in the liquid outer core. That outer core is a moving ocean of electrically conducting iron mixed with other elements. Heat and the slow release of light elements drive convection. Hot material rises, cooler material sinks. Earth's rotation twists and organizes those flows. Moving metal creates electric currents. The currents create a magnetic field, and that field helps sustain the currents. This self-reinforcing process is called the geodynamo. Field lines curve from one magnetic hemisphere to the other. On the side facing the sun, pressure pushes them inward. On the night side, they stretch into a long magnetic tail. That entire region, the field-filled bubble shaped by the solar wind, is the magnetosphere. It is not a solid wall. It is a dynamic interface, constantly flexing, reconnecting, and transferring energy. The sun is always sending out a stream of charged particles, the solar wind. It moves through interplanetary space at hundreds of kilometers per second. When it meets the magnetosphere, a bow shock forms upstream. Much of the flow is diverted around the planet. Some energy enters through reconnection and through the polar regions, where particles can follow field lines downward. Those particles collide with oxygen and nitrogen high in the atmosphere. The atoms absorb energy, then release it as light. We see that light as an aurora, green, red, violet, and sometimes blue, rippling across polar skies. Auroras are beautiful, but they are also a visible trace of a space weather system. The same storms that brighten an aurora can disturb radio propagation, shift satellite orbits by heating the upper atmosphere, and induce currents in long conductors on the ground. Now imagine the internal generator stopping instantly. The field would not vanish everywhere in one perfect frame. Magnetic energy stored around the planet would decay and rearrange. In the first minutes, the solar wind would face a shrinking obstacle. The dayside magnetopause would move closer to Earth, while the tail would become unstable. The first systems to notice would be spacecraft and instruments in space. Satellites rely on the magnetosphere, the atmosphere, and their own shielding in different ways. With less magnetic protection, energetic particles from the sun and from deep space would have a more direct path into near-Earth space. That would not mean every satellite fails at once. Spacecraft are designed for radiation, and exposure depends on orbit, shielding, the solar cycle, and the energy of each particle. But error rates, charging events, solar panel degradation, and damage to sensitive electronics would become more likely. Navigation constellations could lose accuracy or suffer outages during severe solar events. Communications that depend on satellites would become less reliable. The phrase, "all communications go dark," would be wrong. Fiber optic cables do not need a magnetic field to carry light, and local radio systems could continue. But the ionosphere, the electrically active upper atmosphere used by many radio links, would change. Satellite links, timing signals, high-frequency radio, and power infrastructure would be increasingly vulnerable to space weather. The atmosphere is the next question, and this is where responsible science matters. Without a magnetosphere, solar wind particles would strike the upper atmosphere more directly. They could sputter atoms from the exosphere and alter the chemistry of the ionosphere. Solar ultraviolet radiation and energetic particles could also affect ozone and produce temporary changes in atmospheric composition. But the air would not blow away overnight. Gravity still holds the atmosphere. Earth's atmosphere is also protected by its depth, its chemistry, and the energy distribution of the incoming particles. Mars is often used as a warning, but Mars is smaller, colder, and has a different history, gravity, atmosphere, and geology.
Its atmospheric loss cannot be turned into a simple countdown for Earth.
Over very long times, the balance could shift. The rate of atmospheric escape might rise. The result would depend on solar activity, the composition of the upper atmosphere, and whether other induced magnetic effects offered partial protection. Scientists can model parts of this problem, but the exact long-term outcome is uncertain. Near the surface, the most dramatic effect might be in the sky. Particle precipitation would no longer be guided by the same orderly polar funnels. Auroras could appear far from the poles, and their shapes could become broader, patchier, and more directly tied to the changing solar wind. Yet even this picture is not a simple global curtain. The ionosphere can carry electric currents, and Earth can develop induced magnetic fields. A disappearing internal field would remove the main organized shield, but it would not remove every electromagnetic process around the planet. The atmosphere, oceans, ground, and solar wind would continue to interact. People on the ground would not suddenly be exposed to the full vacuum of space. The atmosphere would still absorb much of the harmful radiation. The bigger immediate risks would be to technology, satellites, aviation at high altitude, and astronauts outside the atmosphere. A major solar storm could push those risks sharply higher. What would scientists know, and what would remain unknown? We can measure Earth's field, monitor the solar wind, and simulate how charged particles move through magnetic fields. We understand why a magnetosphere forms and why its boundary responds to pressure. We are less certain about a sudden, complete collapse because nature has never given us a controlled experiment of that kind. Geological records show field reversals and excursions, not a clean switch from full strength to zero. During a reversal, the field becomes more complex and may weaken, but it does not necessarily disappear, and the process unfolds over centuries to thousands of years, not a single afternoon. We also do not know the exact choreography of a field-free Earth. Would the remaining induced currents meaningfully reduce particle access? How would the upper atmosphere respond to different solar cycles? Which technologies would fail first, and how quickly could replacements be protected? The answers would depend on details we can only approximate. There is one more surprising part of the story. The shield is not powered by a battery, and it is not maintained by a solid magnetic core. Its source is motion in a place no human has ever visited. Deep beneath the crust lies the mantle. Beneath that, at about 2,900 kilometers down, is the liquid outer core. At its center is a solid inner core, kept solid by immense pressure, even though it is extremely hot. As the inner core slowly grows, it releases heat and light elements into the liquid surrounding it. Those buoyant flows move conducting metal. Earth's rotation steers the motion into columns and swirls. The result is a planetary-scale electrical machine, a dynamo whose magnetic influence reaches from the core to satellites and auroras. The field we see in a compass needle begins as the motion of molten metal in darkness. So what if it vanished? The sky would not become empty, and Earth would not instantly become another Mars. Instead, a chain reaction would begin. A collapsing magnetosphere, harsher radiation conditions in space, disrupted upper atmosphere chemistry, more difficult satellite and radio operations, and a long, uncertain pressure on atmospheric escape. The most important discovery is the one beneath our feet. Earth's magnetic field is a living consequence of a moving planet. As long as the deep core convects and the dynamo continues, the invisible shield is renewed. Look up at an aurora, watch a satellite cross the night, or feel a compass turn. Each is a different clue to the same hidden engine, an ocean of liquid metal, nearly 3,000 kilometers below us, quietly making a magnetic field that makes modern life safer in space. And that is the real wonder. The shield around Earth begins at the center of Earth.